you from ELECTRON. And first, I would like to introduce Panagiotis Radogrammatikis, who will do a novel presentation of the ELECTRON project. So.
Yeah, screen. Full screen. It's okay. 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 Hello, everyone. Can you see the screen from the remote people? Okay, great. Hello, everyone. I'm Panagiotis Radogrammatikis, Technical Manager of the ELECTRON project. First of all, thank you very much for your participation in this ELECTRON dissemination event. This is an overview presentation regarding the ELECTRON project. I will try to be quick, given that next we'll be able to present more information regarding the use cases and some selected demos. So, just introduction about ELECTRON. ELECTRON is a DS4 project with a budget approximately of 10 million. At the current stage of the project, we have almost finalized all the implementation and integration activities, and we are proceeding to the validation activities in the context of 4 large-scale pilots. The consortium of ELECTRON is composed of more than 30 partners, including energy stakeholders like TSOs, DSOs, technology providers, energy providers, and also partners that focus on standardization and certification activities. And this is the business logic and, let's say, the main pillars related to the architecture of the ELECTRON project. More specifically, the goal of ELECTRON was to create a collaborative framework which will be able to combine both energy-related countermeasures and cybersecurity countermeasures in order to address large-scale cyber physical attacks. So the 4 pillars of ELECTRON is the risk assessment and certification, intrusion detection, mitigation, including both cybersecurity and energy-oriented countermeasures, and finally, training and certification activities. Based on these pillars, ELECTRON is composed of 4 primary conceptual frameworks: the border, cipher, bridge, and prince. Border is responsible for the dynamic risk assessment and certification regarding the integrity of industrial assets. Next, cipher undertakes to detect and correlate potential cybersecurity incidents and compose specific alerts. Next, based on the detection events, bridge covers all the mitigation activities of ELECTRON, including again both security or let's say technology ICT-based countermeasures and electricity-based countermeasures as well. And finally, Prince provides a holistic cybersecurity training framework and certification platform leveraging AR and VR technologies. Some more information regarding the architectural components of its framework I mentioned before. First of all, border is composed of Army, a collaborative risk assessment module, Darcy, which is responsible for the certification of both software and hardware assets, and finally Honeypot as a service, which is a platform combining various honeypots that aim to mitigate potential attacks. Oh, sorry. Next, the cyber framework is composed of several detectors that are organized under the umbrella of a large-scale CM system, the ELECTRON CM system. And as I said earlier, we have implemented several detectors. First of all, FLIDPS, which takes full advantage of a collective intelligence between across several energy stakeholders, thus satisfying, let's say, privacy needs. Also, a remarkable implementation of ELECTRON is the Strongbox component, which can integrate successfully fully homomorphic encryption and AI-based anomaly detection without using the actual data from the stakeholders. And it is worth mentioning here that a relevant patent has been requested by IBM for this implementation. Next, APT Shield, another detector, focuses on APT campaigns, and also Cyber integrates the ELECTRON SharePoint as a MISP repository for cybersecurity information sharing, and ELECTRON Threat Explorer as a CTI, complementary CTI platform that can feed SharePoint and the other components of ELECTRON. After the detection and correlation processes mentioned before, in the context of cyber, Bridge is another framework which is focused on the mitigation actions. Here, I would like to note that the IT-based mitigations rely on the presence of the SDN technology. In particular, through SDN, several mitigation actions can take place, and the most appropriate one, based on the detection events and the risk assessment information, is identified by the NERO component. And next, we have also ISODIN and ELISE that focus on energy based countermeasures in terms of intentional islanding and grid restoration processes. And also, the processes behind these operations are fully supported by the BIP component as a blockchain-based energy sharing center. Let's say this component is responsible for providing information regarding the energy transactions between different stakeholders. Finally, the Prince component, as I said earlier, integrates training and certification activities regarding, let's say, the readiness level of the energy personnel with respect to cybersecurity issues. And for this purpose, we have our goal was to take full advantage of VR and AR technologies, while also other implementations took place within Electron, like a relevant portal, a cybersecurity lighthouse, etc. So, a brief overview of the use cases of Electron follows, and next we will be able to investigate more information about their scenarios, their lessons learned, their practical information from Electron. More specifically here, the first use case is focused on mitigating various cyber attacks. This use case take place in Ukraine and Azerbaijan. It is composed of 5 cooperative scenarios. The first 4 scenarios took place in Ukraine, while the last one will take place in Azerbaijan. More specifically, the first scenario is related to addressing potential spear phishing campaigns using the Prince framework. The second scenario is related to countering, let's say, malware related to the energy sector. Yeah. Okay. Let's say, yeah. Okay. So I'm not going to provide more information. Just a brief overview. Yeah. Okay. Okay. Third scenario related to SCADA cyber attacks. The fourth scenario, unauthorized access attacks, and the last scenario is related to DOS and denial of service attacks. The second use case of Electron is related to cyber attacks against electrical vehicles. We have also generated valuable insights regarding this use case and actual information that will also be publicly available soon, like datasets for AI or any other operations. The third use case focuses on some cyber attacks against wind farms in Spain. And the last one targets the overall transmission and distribution grids based on the Romanian energy chain. And here we also have 5 large-scale scenarios. This is all about the presentation. More information regarding the use cases and their advancements will be presented next. If you have any questions, any comments, please, happy to answer.
Since we are very behind schedule, I propose to start with the demo first, and then if we have time to proceed with the use cases. Yes. So we'll start with the demos first. Sorry. So the first demo, again, so let me, my apologies for this, but I think it's more interesting to show the demos. Presentation to the video. That's on the video. Stop sharing. Το σκρίνο δεν πρέπει, γιατί παίζει πάντα το ίδιο λοιπόν. Για το βίντεο βασικά να πούμε. Το βίντεο είναι κάπου πάνω εκεί, κάτω του ήλιου. Για αυτό ξέρω, δεν ξέρω. Κάτσε να βρω το βίντεο πρώτο. Για αυτό το βίντεο, ok? Okay, so
Okay. Let's start with the demos, and the information regarding the use cases can be presented later. The first demo aims to combine the frameworks mentioned before regarding federated intrusion detection, dynamic risk assessment, and SDR mitigation. It is a collaborative effort between Core Package 3, Core Package 4, and Core Package 5. The overall goal is to mitigate the attacks as fast as possible. Various partners collaborated with each other. For example, University of Western Macedonia, Atos, Ubitech, University of Murcia, Mainz, CERT, and PPC. And the participating components are the Federated Intrusion Detection and Prevention System, the ELECTRON SIEM, Army, Darcy, Nero, and the STM controller. In general, it is worth mentioning that in the context of ELECTRON, we are not focusing on, let's say, typical IT attacks like denial of service, for example, regarding the TCP/IP stack, or let's say well-known attacks. But our goal was to focus on industrial attacks. And that's why we have generated, let's say, relevant data sets that soon all of them will be publicly available in Zenodo and IEEE data port. For example, in this demo, our attention focuses on particular cyber attacks against the OCPP protocol, the Open Charge Point protocol, which is used for the operation of the electrical vehicles. Although OCPP can be considered, let's say, as a secure protocol, there are various attacks that can affect, let's say, the operation of the energy charging platform and the charging stations. And at the moment, there are no, let's say, particular signatures for this protocol regarding well-known IDS like Suricata, Snort, etc. And also, there is no data set for this protocol, or at least for the attacks considered in this case, that can train any AI models. So here you can see the network topology used for this demo. The overall testbed is provided by PPC. And in this case, we are focusing on 2 cyber attacks, while the overall dataset will include 4 cyber attacks. The first one is related to the session establishment denial of service attacks using OCPP application layer packets themselves between the CSMS, the charging station management system, and EVCS, the electrical vehicle charging stations. And the second attack is headbit DOS attacks. Regarding the overall workflow behind this scenario, the first step is the detection of these attacks through the Federated Intrusion Detection Prevention System. Here, I would like to note that the federated training procedure is considered as an offline process, while in this demo, we show only the inference part. The second step is the correlation and normalization of the security events generated by FLIDPS, and ECM, the Electron Security Information and Event Management System, is responsible for this. Next, the security alerts generated by the ECM are processed by both Army, and Darcy for dynamic risk assessment and certification processes. And based on the outcomes of this dynamic risk assessment process, Nero is able to identify the appropriate mitigation actions supported by SDN controller and guide the SDN controller to take the proper action. Finally, through the SDN controller, in this case, the malicious flows are stopped. And some information regarding the impact of this demo. Through federated intelligence, we had a better detection performance instead of, let's say, centralized models. Also, federated learning allows us to counter any privacy issues. New datasets have been generated and will be available in IEEE Dataport and Zenodo. Actually, we have already published a relevant paper for this purpose, and after the publication, this dataset will be publicly available. New specifications have been released in terms of mood files regarding the entities using this protocol. And of course, through the demo, you can see that the attacks are mitigated, let's say, in a timely manner. So let me go ahead with the video.
For this demo, the experimental testbed of PPC will be used. This testbed is also used in the context of use case 2. In this demo, the attacker targets the charging station management system through OCPP attacks. The attacker uses session establishment denial of service attacks that attempt to establish a WebSocket session with the charging station management system. Although the charging station management system is appropriately configured to reject connection attempts from unknown electric vehicle charging stations, the attack can significantly impact the charging station management system's performance. Before showing the various steps of this demo, let's see first the status of PPC SDN experimental testbed through the ELECTRON SDN controller and dashboard. This is the login page of the SDN controller and dashboard. This is the home page of the dashboard, where we can see all connected SDN switches. For this demo, we use one Aruba 2930F SDN switch. By clicking on In, we can see a summary of the switch ports with various information and statistics. Moreover, we also see the connected SDN controllers and the role of each one. The first SDN controller is identified as master. Next, we can see the topology map, which plots all hosts discovered by the SDN controllers. Particular hosts can be inspected in the asset inventory. We now select the host that is targeted by the attacker in this demo. For this host, which is a charging station management platform, we can see various information, like the MUD URL, network details, and running services. Finally, in this page, we can see the flows installed on the SDN switch. Table 0 is the entry point and table 100 contains all the flows inserted by ELECTRON. Now we sort the flows based on priority, so the flows with greater priority are parsed first. Currently, no security rules have been inserted by ELECTRON. Regarding the workflow of this demo, while the attacks are executed, the first steps are the detection and correlation of the security events from FLIDPS and the ELECTRON SIEM. First, FLIDPS is responsible for capturing the network traffic data, generating OCPP flow statistics and detecting the attacks. Next, the security events are transmitted to the ELECTRON SIEM through resyslog. Then, ELECTRON CM is receiving the security events from FLCM and normalizes them. Through the dashboard of the ELECTRON CM, specific details about the normalized events are available to the end user. Next, the ELECTRON CM associates the security events with each other, thus composing security alerts. For this purpose, specific security rules are used. Finally, based on the dashboard of the ELECTRON CM, various information is also available to the end user.
Now we proceed with the presentation of Army component, which is responsible for the initial, but most importantly, the dynamic risk assessment of the topology. Army is based on the holistic project realized by Ubitech. In this part, we are about to see how a new security alarm raised by the ELECTRON CM component triggers a new risk assessment, which is executed on the entire asset topology. On the right-hand side of the screen, we see the dashboard of Army, while on the left-hand side we see the logs of the Army's connector to the events reported by ELECTRON CM. Upon arrival of a new alarm from ELECTRON CM, we observe that a new notification is issued in Army on a specific SDN host asset. This immediately triggers a new risk assessment task being executed in Army. The calculated risk assessment results per asset are published through Kafka to Darcy. The results contain asset information such as the device ID, the computed individual risk level, the associated threats and vulnerabilities, the alarms raised, and the controls that have been applied so far. All this information is used by Darcy to associate mitigation controls with assets. As we see in these terminals, Darcy internally launches two services that calculate the possible mitigation actions to be enforced, depending on either the MUD device identifier or the MUD threat identifier. Both services are displayed on the top left and top right terminals respectively. The computed mitigation controls are expressed in MSPL and published back to Army through a new Kafka message. In the Kafka consumer of Army, we observe the receival of the MSPL messages from Darcy, which triggers the creation of new notifications that record the addition of new mitigation control entries in Army. The addition of the new controls is also depicted in the relevant controls tab. Based on Darcy's response, 3 controls are associated to specific device IDs, and 4 controls are related to specific vulnerability identifiers. By inspecting a control entry, the user notices the MSPL information provided by Darcy. The controls proposed by Darcy are now available to Nero through Army.
The next steps of this demo are to choose the appropriate mitigation action and guide the ELECTRON SDN controller to stop the attack in real time. This is done by Nero and the ELECTRON SDN controller. Nero receives the risk information from Army and Darcy, including a set of potential mitigation actions, and selects the appropriate one. Then, Nero uses the API of the SDN controller in order to execute the mitigation action. Finally, the flow tables are updated by the ELECTRON SDN controller, thus stopping the attacks. For this demo, the experiment
Next presentation, I want to welcome Alan Adil from IBM for the second presentation, that it's the anomaly detection on EV logs using FHE.
This demo shows the use case scenario of privacy-preserving anomaly detection applied on electric vehicle charging transaction logs.
It's fully homomorphic encryption. It's a new quantum-safe encryption scheme that allows the user to encrypt data and still perform computations on the encrypted data. Something that's usually not possible with normal encryption schemes. And the effect you can perform computations over encrypted data means that you can perform privacy-preserving analysis. Right? The user can encrypt the private data, send the encrypted data over to the cloud, and the cloud will go ahead and perform computations without being able to see any data or the results of the computations. So this is FHE. In this project, we'll see actually a demo to see this FHE magic in action. We'll see event logs originating from PPC's electrical vehicles charging stations. Obviously, this is private data. Where this is encrypted in FHE, sent over to the cloud, and the cloud is still able to perform analysis over this encrypted data, and specifically time series analysis, and is able to detect anomalies or possible attacks on the charging stations by analyzing these data. So let's see the demo.
This demo shows the use case scenario of privacy-preserving anomaly detection applied on electric vehicle charging transaction logs. During the charging process of electric vehicles, the Open Charge Point Protocol, or OCPP, is utilized by the charging stations in order to transmit measurements that indicate the energy consumption during the charging process. These measurements are used by the charging station operator for billing the charging session. However, the charging process is vulnerable to cyber attacks, since the electricity measurements are transmitted unencrypted and unsigned. There are also privacy concerns, since the electric vehicle charging data is considered private information, risking potential eavesdropping and profiling of energy usage by malicious actors. In this demo, a cyber attacker performs an energy theft attack by altering the OCPP meter values messages transmitted by the charging station to the charging station operator. The cyber attacker modifies the watt-hours values in the meter values messages transmitted during a charging transaction, aiming to reduce the total billing amount of the charging transaction. In order for the tampering to be detected, the electric vehicle charging curves should be analyzed for potential deviations. To deal with the potential tampering of EV charging data, a privacy-preserving anomaly detection solution is applied by ELECTRON. In more detail, PPC, which is the charging station operator, submits periodically EV charging transaction logs to IBM for analysis. After encrypting the logs, they undergo analysis by the fully homomorphic encryption, or FHE, anomaly detection module of IBM for potential tampering, utilizing the autoregressive integrated moving average method. If an anomaly is detected, the FHE anomaly detection module generates an encrypted security alert, which is delivered to the ELECTRON Security Information and Event Management System, which in turn decrypts the alert and visualizes it on the dashboard, thus notifying the security administrator for the potential anomaly. The scenario is initialized by setting up the digital certificates necessary for the FHE anomaly detection module to verify and authenticate the digital signatures used to ensure the integrity of the EV charging logs. The certificates have been sent to the IBM team via email. The certificates are in binary format, however, we can open a certificate and see how it looks like. Now that the certificates are configured, the FHE anomaly detection component is ready to receive new EV charging logs. In this screen, you can see the command line terminal of the charging station management system. It is a web-based software platform that handles and authorizes the EV charging transactions. Moreover, this system receives the electricity measurements during each transaction. At the end of each charging session, the charging station management system will upload the measurements log file to the IBM Cloud Object Storage, in order to be received by the log aggregator and the FHE. On the right terminal, we are starting the IBM Cloud Object Storage monitor process, which automatically uploads new log files to the cloud. On the left terminal, we will copy a log file of a completed transaction to the monitored folder. Since this is the first log we are submitting, this is considered normal by default, and will be used by FHE to get the baseline and train the ARIMA model. On the IBM side, the IBM Cloud Object Storage Receiver downloads the new log file and subsequently deletes it from the cloud storage. A subcomponent of the FHE module passes the JSON file and converts it to CSV format. Here we see the log aggregator component, which takes the CSV file and aggregates the data to create an encrypted log utilizing the FHE method. The aggregator encrypted the log and signed it with the digital signature shown at the beginning of the demo. Next, the FHE anomaly detection module sees that a new encrypted log has been saved, and it starts to apply analysis on the encrypted log. Because this is the first log, it is considered non-anomalous by default. It is used to train the ARIMA model and check if future logs contain any anomaly. Returning back to the charging station management system, now we are going to send a charging transaction log, which contains meter values that have been tampered with. On the IBM side, we see that the receiver module has received the log file and then has deleted it from the cloud storage. As usual, the JSON log file is converted into CSV format, and the aggregator aggregates, encrypts, signs, and saves the log file. Next, the FHE anomaly detection module gets the encrypted log and authenticates successfully the log's digital signature, indicating the valid integrity of the log file. Once the signature verification is successful, the analyzer proceeds with checking the log file for potential anomalies. Now, this is the part where all of the FHE computations happen. The analyzer receives and analyzes an encrypted log that it cannot actually see. However, due to the FHE encryption, the analyzer is able to apply computations on the encrypted data without any need to decrypt this data. So, the ARIMA model is trained on encrypted data, and then is used to detect anomalies on subsequent encrypted data. The analyzer has now finished with the computations, and it produced an encrypted report, which specifies whether any anomalies have been detected. This encrypted report is saved and signed, and will be sent to the alert decryptor of the ELECTRON Security Information and Event Management System. It should be noted that, for the demo purposes, we used a less secure encryption in order to make the computations run faster. We could also run on fully secure encryption, but it would have taken several minutes to complete the computations and produce the detection results. Finally, moving to the ELECTRON Security Information and Event Management System, we are logging to the dashboard of the tool in order to see the contents of the security report generated by the FHE detector. All the security reports are sent to the SIEM agent, which validates and normalizes all the information. In this page, we can see all the normalized events that have been received from the FHE detector module. By opening a security event, we can see various useful information. For example, we see the raw log corresponding to the security event. The raw log is constructed by the FHE module and is the main source for constructing the normalized event. We can see the date when the anomaly was detected. We also see the type and category of the event. We also have the data source, which indicates the ELECTRON component that generated the security event. We also have information related to the network, like the IP address. In this case, based on the OCPP logs, we provide as victim the IP address of the EV charging station. This aims to help the security administrator to identify and narrow down the compromised communication channel. Finally, we have information specific to the sensor that is placed in the user data fields. In those fields, we have the ID tag, which is the RFID tag used as identification by the EV user. The RFID tag is used by the EV user in order to get authorization for a charging transaction and to be billed accordingly. This is a very sensitive information, and can be used to reveal the identity of an EV user, and associate them with private EV charging data. Then, we have the transaction ID, which is the unique ID of the transaction within the charging station management system. We also have the expected value of the state of charge, as well as the actual value that was observed by the FHE analyzer. Moreover, we also have the state of charge range, which indicates the particular part of the charging curve where the anomaly was detected.
For this demo, the experimental testbed of PPC will be used. This testbed is also used in the context of use case 2. In this demo, the attacker targets the charging station management system.
So next demo presentation, it's Antonis Bulgaridis from CERT that are hosting this event, and we'll proceed with anything.
Give me a sec. All right. Hello, everyone. This is Antonis Bulgaridis from CERT. For this scenario, we are handling the proactive configuration, energy balancing, and grid restoration parts, which is part of use case number 4, scenario number 5. The leader of this collaborative scenario is CERT, and the contributors towards it is UCY and Isodrol. So an outline of this, let's say, short demonstration is that, first of all, we are going to introduce the scenario, let's say, more or less put how, let's say, the components of ELECTRON are collaborating towards completing the scenario, then shortly the scenario flow, and then I'll press the play button to the video and let the speaker explain the rest. So for this scenario, we are having the assumption that a critical large-scale attack is in place, and then proactive reconfiguration procedure is activated as a remediation step, while energy balancing is assured throughout the process until the grid is restored from such an attack. The components involved, as can be seen in the right-hand side, are Isodin, that does the grid, let's say, reconfiguration suggestions, ELIS that calculates the optimal schedule, BIM that performs the energy transactions, and of course, let's say, of course, user-wise sandboxing environment, which in this case, let's say, serves as the test bed itself that we tried this scenario on. A little bit about the sequence. We are working on firstly on normal grid operation when we are, let's say, using a list to read the, let's say, measurements and grid configuration from the sandboxing environment. We are using a middleware, ThinkSpeak agent to, let's say, communicate all the read writes of the measurements throughout the flow, and then send the unit commitment schedule to the energy transaction component, which is BIM, but also writes the PVs and the optimal set points back to the ThinkSpeak component, and then the operator, which, I mean, in this case is the sandbox environment, reads the updated set points and write back the measurement and so on and so forth. This is the normal grid operation. There is then, let's say, this attack that occurs in one of the buses of the topology. From Isodin, we are getting some, let's say, updated grid configuration back to the sandboxing environment. These, let's say, updated grid configuration measurements are being forwarded to ELISE, which in its turn calculate again the optimal, let's say, set points based on this attack that occurred, and write back these endpoints to the sandboxing environment. Then the operator, let's say, accepts or declines the changes that were proposed, and we move from the abnormal grid operation to, I think it's this one, to the grid restoration part, where Isodin then informs that the attack is cleared. The DSO performs the actions for restoring the grid back in its initial state, and then ELISE again recalculates the optimal set points. And in a way, we started from a normal operation. We, let's say, received the attack, we handled it, and isolate the parts of the network that were critical, and we needed to let's say, to not let it cascade as an effect to the whole microgrid. And then during all these operations, BIM can start the energy market and perform the energy transactions based on the optimal schedule each time. For all these read and write operations, again, as I said, we used ThinkSpeak component right in the middle for the communications. This is more or less the video, the scenario workflow. I mean, we've prepared a short demo. It's 3 minutes, more or less. I try to share it through there. Please, from the online audience, in case you cannot hear the sound, let me know so I can, let's say, use an external media player to play the video. So,
during normal operation, the DSO monitors the operation and power flow exchange between the main power grid and the 3 grid-connected nanogrids through the use of the graphical user interface of the sandboxing environment. Then, ELISE calculates the optimal power exchange between the main grid and each of the nanogrids and sends the optimal set points for controlling the battery storage systems, charge or discharge state, to the sandboxing environment. We then move to the attack phase, where we assume that a critical cyber attack was detected within the network station, serving the power substation number 5. To avoid any propagation of the cyber attack, Isodin component sends to the DSO, in this case the sandboxing environment, a warning message and viability suggestions for optimal configuration of the grid in order to minimize as much as possible the amount of load not served. Then, the DSO accepts the suggestions coming from the Isodin component and performs the reconfiguration of the grid by changing the status of the circuit breakers as indicated by the change of colors in the graphical user interface of the sandboxing environment. While monitoring the microgrid, ELISE detects the change in the circuit breaker status that results into a topology reconfiguration and calculates the new set points for the battery storage systems and send them back to the sandboxing environment through the ThinkSpeak communication channels. When the attack is cleared, Isodin component sends viability suggestion for restoring the grid reconfiguration to its normal operation conditions. Following these suggestions, the DSO performs the needed breaker status updates, as again indicated by the change of colors in the graphical user interface of the sandboxing environment. As previously, during the microgrid monitoring, ELISE detects another change in the breaker status that results into another topology reconfiguration by reading the updated status of the breakers from the ThinkSpeak communication channels, and once again calculates the optimal set points for the battery storage system units. The updated set points are then sent back to the sandboxing environment and visualized through the graphical user interface. Finally, The last step of the whole procedure is that we enter the energy transaction stage, where ELIS sends the unit commitment schedule to the BIM component, and in its turn, BIM starts the inter and intra microgrid energy markets and performs the energy transactions. Thank you very much for your attention.
So that was it. Thanks again for the attention, and if you have any questions, I'm happy to give it a try. All right. Thank you.
So thank you, James, once more for the presentation. So let's move to the next demo. It's the ELECTRON CTI platform. It's Christoph Sutansky from Atos that will do the presentation. Yes. Okay, you can. I will do the demo. Okay. My hands to work with the. Okay. Don't worry, I will find your room here. Thank you very much. There you go. Yes.
Hey, thank you very much. It's also my turn today, almost the last turn. So if there's still any interest on CTI solutions, so part of the whole ELECTRON story also regards and touches on the CTI. So we have our, let's call it CTI platform, where we already have collected useful information for other projects, for synergies, and etc. It's a joint work between Evidon, myself, Esteban Armas, my colleague, and IDENER, Pablo Guerrero from IDENER. So let's just go quickly to the main point for the demo. So the ELECTRON CTI platform composed of two main functional blocks that you see. One is the CTI SharePoint code that is actually, you expect, allows to share CTI data with the additional information that it's provide additional functionalities about anonymization and security enhanced confidentiality sharing, where you can confidentially share data with selected stakeholders in the electrical power energy system domain. And we also have a Threat Explorer, which is actually a component which allows us to have the open source intelligence information from databases external that are periodically discovered vulnerabilities and fed to our SharePoint. So the main aspect is that we have the MISP, the MISP technology for interconnecting. This is also auto standard technology used nowadays for interconnecting entities for sharing data. So we adopted this in the backend. In the front end, we have a front end, which is a functional dashboard for enhancing security sharing and anonymization and encryption. It's also interesting because we have also do CTI enrichment. This is information that how much when you receive a vulnerability, how much this vulnerability is relevant for an infrastructure operator assets, topology, etc. So this relevance and impact of vulnerability to a specific infrastructure operator, it's also a useful functionality. So for the ELECTRON Threat Explorer, so we have this daily vulnerabilities retrieval from the open source intelligence databases. Then that is fed to the SharePoint. It's enriched with information about the power grid domain with the possible cyber attacks that can be taken based on these vulnerabilities, in which, for instance, our project can detect and mitigate. So that information is also given to the vulnerability objects. And importantly, we are very specialized. So our CTI pattern is specialized for vulnerabilities in power grid domain. It's not about generic malware vulnerability, but for specific vulnerabilities which can be exploited for the power grid domain. You see some info soon. So surprisingly, we actually have more than around 600 vulnerabilities already collected, in which we're interested to share with other peer stakeholders in the domain. These are available and we curated this, so we tagged additionally, so that's facilitate the processability of this vulnerability information. So we'll see in a while. We are based on keyword expression for the moment. We have also strength of work for using machine learning. And the interesting part here is that surprisingly, we've selected keywords very specific to the power domain. So you see the industrial control protocol, Modbus, IC104, DNP3, 61850, OCCP, Profinet, PLC, logic control. So these are all specific, very specific keywords for the domain. But based even on that, we have around 600 vulnerabilities, which we believe are very specific for the domain, but useful in added value. And this is our distinguishability from other activities we've seen so far, where surprisingly for us, they have rather high level vulnerability information and threat information. But when talks about specific power grids, digital substation, device vulnerability, we didn't find in the red databases, well, from the other sharing platforms, this information. So this is available in our system. In ELECTRON, this is the list of other sources we've curated. This the principle is the first vulnerabilities for the project that has been found in one of these references. We tagged and we take this as a reference for us to be on a daily basis crawled. We have crawlers in the backend, which on 24-hour basis scroll for these open databases and feed our system periodically with daily basis with new vulnerabilities on these keywords we've seen there. Right, so this is basically the highlight of the platform. My colleague Esteban can give you a few more highlights of the functional aspects, and then we'll give you an online demo. We don't have video, but I hope you appreciate some hands-on this.
Okay, thank you, Risto. All right, so as my colleague just explained, the Electron SharePoint provides two main functionalities, basically the option of adding a new layer of sharing capabilities to the MIST platform and the enrichment of flash scoring of vulnerability events coming from the Threat Explorer. On the demo, I will try to simulate basically the behavior of the Threat Explorer by receiving an event that is already there, but just to calculate the I'm sorry. That's what happened when the light dims, you know. Just a minute. Okay. Let's go with the sharing capability. So basically, let's start with the Alice and Bob example, the most classical example of sharing a secret. Okay. For this, we create this dashboard, this system that provides this extra sharing capability layer to the MIST platform itself. We have the MIST instance here of Electron, and then we can access as Alice to the system. And we are trying to share an event to our friend Bob. Okay, so let's upload an event with some IP addresses that we detect that could be malicious, and then include in the event description something that can be quite sensitive. So let's say the sensitive information. So we want to encrypt this. Also, we want to add any number of tags that we think that could be useful for the receiver. Then we want to share this event to whether it's an user, an organization, a role, or a multiple end users as well. So let's share this information with Bob. And let's modify the different attributes. In this case, I want to encrypt this IP address. I want to anonymize this other one. I want to leave this one in plain text, and I want to put this another one in
as an encrypted IP address. Okay, so once that we already do that, we also can define a time window in which the receiver will be able to look at the event that we are going to share. So basically, me as Alice, I will say that I want to Bob to be able to look into this event between today and tomorrow, for example. And by Friday, Bob won't be able to receive or to read any of this information. So on the MISP instance, we will have this event with the information encrypted as we asked to do that. In this case, we have these two IP addresses encrypted, one anonymized and the second one in plain text, and the fourth one, sorry, in plain text. But when I go to the Bob account, I will see that I have a new event coming from Alice, which show the ID of the event, which is the one that is here, the information that is in the MISP instance and in the other instances that are connected to this one, encrypted in plain text in my case. And if I want to go there and read what is encrypted, in this case, the IP addresses that I asked to be encrypted, I can read it without any issue. I can do that, as I say, on different types, attributes, objects of MISP. Basically, we cover these different objects in terms of anonymization and encryption. And in the term of the scoring, yes, I would like to show how we calculate and add and enrich the event. So in this case, we have this event, okay, that is not already scored and doesn't have anything enriched, and published to the CRM queue that we use automatically. So this behavior is basically automatically from the Thread Explorer. We receive this event and automatically we calculate this thread score. So as you can see here, there is this taxonomy, this tag add to the event. We calculate the score between 1 and 5, being 5 the highest and the riskiest. And we also map the infrastructure that we have, that we receive from other components. So we can also put it by hand, let's say, in the system, and we map those components to the vulnerability and detect the risk of those different components, particularly with this vulnerability. So in the logs, well, the logs doesn't show anything right now. Sorry about that. But basically, automatically, we are able to calculate the risk, map to the affected infrastructure nodes, and also we provide a security layer that is not already in place in MISP, giving the organization the possibility to share sensitive information not only with another organization, but also with particular users and particular roles of a different connected MISP instances. So that will be everything from my side. I don't know if you have any questions. No? All right. Thank you.
Thank you both. So we continue with the next demo. It's a presentation of the print framework. Okay, so let me find the correct.
Welcome to the demonstration.
Hello, everyone. My name is Thomas Lagas. I'm assistant professor at the Demokritos University of Thrace. And I'm going to show you one of the frameworks of the ELECTRON project called PRINCE, which is responsible for training using augmented reality and virtual reality technologies. I will not go through the introductory stuff because actually we're running out of time. So I will go to something that I believe you will find more interesting. And this is the demonstration video of the portal. So without wasting any more time, I will go straight to the video, and I hope you enjoy it.
Demonstration video of the PRINCE framework. PRINCE is the training and certification framework on cybersecurity awareness, developed in the context of Work Package 6 of the ELECTRON project. To begin the demonstration of our scenario, let's access the URL link of the PRINCE portal. Initially, an energy, power, and energy system employee registers for an account in the portal by providing some essential information. Then, with the registered credentials, the user logs into the platform and depending on their role, for example security administrator, they enroll in the respective course. Of the PRINCE framework. PRINCE is the training and certification framework on cybersecurity awareness, developed in the context of Work Package 6 of the ELECTRON project. To begin the demonstration of our scenario, let's access the URL link of the PRINCE portal. Initially, an energy, power, and energy system employee registers for an account in the portal by providing some essential information. Then, with the registered credentials, the user logs into the platform and depending on their role, for example security administrator, they enroll in the respective course. Following the example of the Cybersecurity Awareness for Security Administrators course, the trainee is called to complete for topics corresponding to threats on phishing, denial of service, spoofing, and unauthorized activities, with interactive theoretical and practical material. Then, the trainee can proceed by practicing their gained knowledge through the section of cyber exercises and complete the course with the respective certification exam. At the beginning of the course, the trainees can find some introductory information on the course's scope, as well as a study guide, instructions on how to use the AR Tutor, KROX, and Process AR tools, an announcements discussions board, and a chat room for real-time conversations. Let's go through the phishing course as the first indicative example for the functionality of the PRINCE portal. Through the specific course, trainees will learn how to detect, prevent, and respond to different types of phishing attacks. First step of the training experience is a thorough presentation, enhanced with narration features and powered by the AR Tutor tool. Starting with the phishing presentation, the trainee can utilize the AR Tutor mobile application to scan the presentation's QR code, download different types of augmentations that will support their learning experience, and display them by pointing their camera to the signified positions of the slides. Throughout the presentation, there are available URL link augmentations redirecting the trainee to pop quizzes within the application's environment in order to test their understanding of the theoretical knowledge acquired on the previous slides. The trainee can fully interact with all of the presentation's augmentations through simple finger gestures. Specifically, pinching to zoom in or zoom out, tapping to play or pause videos and audio files, and sliding for rotations.
Ensuring a safer digital environment.
Sandboxing is a security technique that isolates programs or processes from each other and the underlying system.
Once an activity is completed, it will be enabled to be marked as done as part of the trainee's progress within the course. Upon completion of the presentation, the trainee can access additional material on related lecture notes, suggested further reading, and a self-assessment questionnaire on phishing. Next step in the trainee's learning experience is the utilization of the Process AR tool. For the respective example, we will move to the Denial of Service module, where trainees will acquire knowledge on different types of DOS attacks, their concepts and anatomy, as well as protective measures. Through the respective exercises, the users are asked to identify data from servers in augmented reality panels. First, they have to calibrate the environment to interact with QR codes, and to load the panels, they should click on the QR button and focus the camera on them. The particular example prints logs from the console and depicts a list of active connections interacting with the server. Specifically, the objective is to identify which machine receives a DOS attack. Each machine must have its own QR code linked. As we can see, the second machine shows symptoms of having a SYN flood DOS attack. AR panels can show quick information and use it simultaneously. Let's move on to a VR-based exercise on the Kerox tool. For the specific exercise, the trainee wears a VR headset in order to interact with the virtual environment. By wearing the helmet and holding the controllers, the trainee can look around and interact with the icons that are presented in front of them. The respective icons provide valuable information that will assist trainees in solving the provided question. If the answer is correct, a new stage begins that may take place in a different location of the virtual environment. Overall, the main purpose of the Kerox tool is to place users in a training environment that simulates real-life situations with gamified principles that will further enhance their learning experience. If the trainee fails to answer the question correctly, a notification sound is played to signal them to proceed for another attempt. Once the trainee completes the different learning modules, they can proceed to the cybersecurity exercises section to practice their acquired knowledge. When the trainee enters an exercise, an avatar is displayed on their screen, explaining the upcoming challenge that they need to resolve. Also, the avatar is integrated with AR capabilities, making it possible for the trainee to display it through their mobile device.
Identify this information flow and determine which API MAC pair corresponds to the scanner.
Then the trainee can proceed to the Cyber Range platform for the resolution of exercises while utilizing two different tools. The first one is the Root the Box tool, which requires the trainee's registration and logging in. This tool contains a set of exercises called missions, with each mission having a thorough description of its context and objectives, and a set of questions called flags, with included hints on questions of high difficulty. To answer a flag, the trainee registers their answer through the Submit button, with a system notification of whether they answered correctly or not. To answer a question correctly, the trainee must access a second tool, the dashboard, which receives real-time network traffic from the Technalia substation, presented in a graphical and organized manner, and allows the trainee to filter the data in order to answer the questions. In addition, trainees can monitor the progress of other participants through the respective scoreboard. When trainees complete all of the course activities, they can proceed by taking the certification test and the practical assessment through the Cyber Range platform. Starting with the certification test, a summary page is presented to the trainee, showing their progress on any potential attempts on taking the exam. Specifically, the certification exam consists of a collection of multiple-choice questions based on the knowledge acquired throughout the course's modules and requires a minimum of 70% as a passing grade. After successful passing of the exam, the trainee can proceed by completing the practical assessment. In a similar manner to the Cyber Range exercises completed for the previous modules of the course, the trainee is asked to complete a mission while utilizing once again the Root the Box and dashboard components. After careful checking of the instructions, the trainee accesses the dashboard component to filter the required traffic data and figure out the correct answer for the exercise, and then returns to the Root the Box component to submit the answer to the respective flag. Considering the passing of the exam and the successful completion of the practical assessment, an assigned certificate in PDF format is issued to the trainee, which can be then submitted for an official signature by the certification authority, that is in our case Technalia. Thank you very much for your attention to the demonstration of the Prince framework. Welcome to the demonstration video of the Prince framework. Prince is the training and certification.
Okay, so that was it. Thank you very much. If you have any comments or questions, you can contact me. Thank you.
So for the final presentation, it's about the Electron Lighthouse. And we have with us Jesus Rosario Mate. It's from TUV Spain. The video. Okay, so we will start directly with the video.
This is a demo for the dissemination event of Thessaloniki at the ELECTRON Cybersecurity Lighthouse. The main page contains the logo that is going to have the portal and the main objectives of the web portal. The next window contains information, the objectives, and the link of the ELECTRON project. Then the web portal subdivides into three main sections. The first one is the current European energy policy that contains the main organizations related to cybersecurity. It contains ENISA, ECCC, ENTSOE, ASA, EEISAC, Bridge Initiative, ETIP-SNET, ECSO, and EUCC. In the ENISA section, you can see, apart from the information, you can see how it is organized and the link to its official web page for additional information. Another section is the EUCC one, that as well as the ENISA one, you can see information of the organization and as well information about common criteria and its official links. The next section is the European Union Acts and Directives, where you can find the Cybersecurity Act, NIS2 Directive, CER Directive, Network Code on Cybersecurity and the Cybersecurity part of the Red Directive. For example, the NIS2 Directive shows information, objectives, and main provisions related to cybersecurity in the energy sector and two links at the bottom of the page that redirects to more information and documentation. The same for the Red Directive that shows information of the three new cybersecurity parts that have been incorporated recently with its requirements and mechanisms, and below its links. The final main section is the main standards, which contains the main standards to ensure a secure environment in the energy sector like IEC 62443, ISO 15408, ISO 18045, ISO 22301, ISO 27001, ETSI 303645, and IEC 62351. For the IEC 62443, as the other sections mentioned before, contains information of the standard and a link to have more information. The same for the ISO 27001, which shows its importance in every aspect of cybersecurity in all kinds of business and sectors. The portal contains a section of the most frequent asked questions that the users may have while reading the content of the web portal. Here they will be able to resolve some of those doubts or questions they might have. Another feature that the web portal contains is a forum in which users can have discussions or open topics related to cybersecurity and share their opinions. To do so, the user must have been registered and logged in the web portal. To register is quite easy. You only have to set a username, your email, and your password. When you finally have registered, you will be redirected to the home page, and at the top corner, you can see that you have your username. If you click on your username, there will be two options. One is to log out and the other is to see your profile. There you will be able to change some parameters like your name, password, to log with double authentication, see where your account is currently logged, and also if you want to delete your account. Going back to the forum section, a new button appears. This button is to create a category for initiating a thread about a topic. You will need to provide a name for the category, a brief description. Also, you can customize with some colors and some other setting parameters. Once the category has been created, we can start a new thread. Again, you will need to provide a name and a brief description of the topic you want to start talking about. Once it is done, click on the button Create and your thread is going to be visible for everyone. You will see that the thread don't have any interactions. To verify that this thread is visible to everyone, I will create another user and going to reply to his open topic. Going to the forum section with the new user. Go to the top section in the navigation bar to the section Recent Threads. There you will see the thread created previously. To reply that post, click on the blue button that says Reply. There you will be able to write your opinion on that topic. Now the user 1 can see your comment and replay back if he wants. Another additional feature is that you can delete your comment if you want. Finally, you can see that the thread created previously have one replay.
Welcome to the demonstration video of the PRINCE framework. PRINCE is the training and certification framework on cybersecurity awareness, developed in the context of Work Package 6 of the ELECTRON project. To begin the
demo concluded the session of the demos. It was the last presentation for today. I want to thank you all for presence audience that stayed with us all these hours. If we don't have any question or any comment, we can conclude the session. Okay, so we have circulated in the chat a link for a short questionnaire in order to get some feedback out of you. So it's like most 5 minutes it will take for your time to complete the questionnaire. And this information will be very useful for us. It will be used in some of the upcoming deliverables regarding the exploitation of the ELECTRON solutions. So if you can spend 5 minutes of your time and complete this questionnaire, it will be very useful for us. I want again to thank you all and see you in the next event that we are going to have. Thank you all. Bye-bye.